Welcome back to my channel. Today in this video lecture we will learn about the constraints. So the constraints are quite important in classical mechanics and also for the students of physics, MSc physics. Okay, now let's read what do we mean by constraints. The limitations on the system, the limitations on the motion of the system are called constraints, and the motion is said to be constrained motion. So let me explain. Let's take the example. Okay, so this is a very good example. You can see that this is the bead and this is the wire. Now the bead can only move along the wire. Okay, and the bead cannot go in this direction and bead cannot go in this direction. Okay, so the motion of the bead is now limited in the straight path only. Okay, so that means that the bead, and that means we will say that we have imposed some limitations or constraints on the motion of the bead. Okay, and now the motion of the bead is called the constrained motion. So I hope you have got the idea of constraints. Okay, so constraints just means the limitations. Okay, okay, now we will read about the types of constraints. There are two important types of constraints. One is the holonomic and other is the non-holonomic. Okay, of course there are several other types of constraints also, but we will read only this type of constraints. Okay, so these constraints can be expressed in the form of equation of the form. Okay, so the constraints which can be expressed in the equation of this form, okay, are called are called holonomic constraints. Okay, so let's take the example. So for example, if r is the position vector of a particle at any angular coordinate theta, so what you have to do is that you have to look closely and carefully at this diagram. This is the particle p, this is the origin o, this is the angular coordinate theta, this is the position vector of the p. Now if we fix the magnitude of r, okay, if we fix the magnitude of r, that is we will make the magnitude of r constant, that is the magnitude of r equals to a constant. Okay, then and only theta can change. Okay, and we will only allow the theta to be changed. Then what will happen? Then you can easily simply understand that equation 3, this is the equation number 2. Then equation 2 expresses the constraint for a system in circular way. That means that in that condition this equation will represent the constraint for the motion of this particle p, and due to this constraint the motion of the particle p will be the circular motion. Okay, that means p will trace the circle, and that circle is x square plus y square equals to a square. Okay, so this is the equation of the constraint which has the same form as written here. Okay, okay, now let's read what are non-holonomic constraints. Okay, the constraints which cannot be expressed in the form of equation 1 are called non-holonomic constraints. That means the constraints which cannot be expressed, that means I will repeat, the constraints which cannot be expressed like this equation, so those constraints are called non-holonomic. Okay, so let's look at the example. For example, the motion of a particle placed on the surface of a sphere of radius a. Okay, so it's very simple. This is the sphere. Okay, so this is the sphere. Okay, and if we place the particle p on this sphere, then of course this particle p cannot go inside the sphere. Okay, this particle p cannot go inside this sphere. Okay, and it can move only outside the sphere. Okay, either on the surface of the sphere or outside the surface of the sphere. That means that the position vector r may be equals to the radius. That means the magnitude of the position vector r may be equals to the radius of the sphere a, or equals to or greater than the radius of the sphere. Okay, so this type of constraint has the inequality. Okay, also, so if there is a greater than sign, so this type of constraints are called non-holonomic constraints. Okay. Okay friends, thanks for watching this video. If you like this video, then please share with your friends, like this video, and thanks for your support. Okay, thank you very much.